In section 2.3, we're going to look at analyzing graphs of functions. The graph of a function f is the collection of ordered pairs of the form x comma f of x such that x is in the domain of f. Another way to kind of say this is that an ordered pair will be on the graph of the function if it satisfies the equation y equals to f of x. So kind of like what you've seen in the past, where a lot of the graphs you've done, whether they be lines or other objects, were of the form y equals. Now that we're working with functions, instead of calling it y, we use the functional notation f of x. The way this works, for example, is we're going to be able to find the value of a function from its graph if you pick any x value. Okay, so let's suppose I want to find the value for f of x. And in this case, let's find the value for f of 1. Remember, the ordered pairs are going to be of the form x comma f of x. So to find the value for 1, what I need to do is find the ordered pair on the graph whose x coordinate is equal to 1. If I look for where x is 1, that's going to be right here. I now locate the graph by going either up or down. We go right here. This is the point on the graph. So this is going to be the point that's going to have an x coordinate of 1. And then to find the corresponding y value, we just trace it over to the y-axis. And it's not going to be exact. Let me just say about 1.8. So we're just going to ballpark it here. So f of 1 would have the value 1.8. Okay. So this is going to be the very first thing we're going to do. And it's a very important skill to be able to have, is to find the value of a function from its graph. The graph of a function is the collection of all ordered pairs of the form x comma y such that y is equal to f of x. As we've seen before, we can write these ordered pairs now as x comma f of x using our function notation. Let's look at an example. For example, let's suppose that this is the graph of some function. Let's say it's y equals to f of x. If we look off of the graph, we can see that the value of f of negative 3 is going to be equal to 1. The reason for that is when x is negative 3, that's right here. So here's x equals to negative 3. We locate the point on the graph that corresponds to that x value by either going up or down. Here we have to go up, and then what we do is we trace it over to the y-axis, and we see that that has a y value of 1. Therefore, f of negative 3 equals to 1. Similarly, if we take a look at the value for f of negative 1, we have negative 1 we're plugging into the function. When x is negative 1, we would be right here. We then either trace it up or down to locate the point on the graph. So the point above negative 1 is right here. And then we go over to the y-axis to get the function value. And so that's going to have the value equal to 3. Let's take a look at another concrete example. For instance, if we look at the value of the function f of 1, here the input is 1, so we have an x value of 1. When x equals to 1, we're right here. We locate the point on the graph, which is here, trace it over to the y-axis, and we get a value of 2. So f of 1 equals 2. Let's do one more actually. Let's do f of 2. To find the value for f of 2, this time we see that the x value is 2, so we're plugging 2 in. And notice that this is the graph is actually right on the x-axis. So if we trace that over to the y-axis, that's going to be a y height or a y value of 0. So f of 2 is equal to 0. Let's now take a look at two more examples. In example 1, we're asked to find the value of each function from the graph below. For example, f of negative 2. f of negative 2, when x equals to negative 2, that's right here. We locate the point on the graph, which is here, trace it over to the y-axis, and we get the f of negative 2 is equal to negative 2. For the value of f of negative 1 is right here on the x-axis. We locate it, we trace it up, the point is here, we go over, and we get a value equal to 3. Okay. F of 0, so when x is 0, we're right here. We trace it up to find the curve, which is right here. And now it's not quite exactly 1. It's kind of in between 0 and 1. So you can approximate it, give your best guess. I don't know, maybe I'll say about 0.8. As long as it's reasonable, especially if it's not exact due to the scale of the y-axis. I would certainly accept it's certainly more than halfway closer to 1. So, anything realistically greater than 0.5 and less than 1 seems like a good answer for f of 0 there. If we look for the value f of 2, when x equals to 2, we're right here. We locate the curve by going up. This is the point on the graph. Then over to the y-axis to get the value 4. So f of 2 equals to 4. Let's take a look at the next one. We have the graph of a function. The function is called g of x. They want us to find the value of g of negative 4. When x is negative 4, that's right here. We trace it down to find the graph is at this height. And then over on the y-axis, we see that that's at a height of negative 3. So g of negative 4 equals negative 3. Let's do the next one. G of negative 3. So when x is negative 3, that's right here. That point is on the x-axis, and that has a y value it's equal to 0. So g of negative 3 equals 0. These are important points, and we talked about these in the last section, but those places, there's a couple of them in this example. The places where the graph crosses the x-axis, excuse me, those are referred to as x-intercepts. They're also called zeros of the function because those are the x values that produce an output or a function value equal to 0. The next thing we want to do is we want to evaluate g of 0. When x equals to 0, that's right here. We trace it up to the graph is right there, and we get the value g of 0 equals to 1. We have one more. We want to find the value for g of 2. When x equals to 2, that's right here. We trace it up to the graph, and then trace it over to the y-axis. Again, this is one that's not going to be exact. It's somewhere between 1 and 2. Use your best judgment. Usually we should probably say the approximately equals 2, but to me it looks to be about like halfway between, so I'll call it 1.5. The first important skill, being able to read a graph and determine the function values. The next important skill set we're going to have, which is very important, is the ability to identify the domain and the range from a function's graph. Okay. So going back a little bit, remember we had the x values. So if you remember our ordered pairs from before, remember our ordered pairs are the form x comma y, where x corresponded to the domain set, and then the y values corresponded to the range set. Okay. Now we know that instead of calling them y equals, usually we're calling them f of x, but it's the same thing. So in essence, when we're looking for the domain, we're going to be looking on the x values of the graph. So what values can we actually plug in? In other words, what portion of the x-axis do we have parts of the curve above? When we're talking about the range, then you're going to be looking on the y-axis and the y-scale, okay? Easy way to kind of keep them memorized. Again, think alphabetical order. X comes before y. Alphabetically, domain would come before range. So the domain is the x values. The range will be the y values. Okay? So the domain, again, that's a set of inputs. Those will be found on the x-axis. And the range is the set of outputs, which is going to be found on the y-axis. Another kind of tip that I think is oftentimes very helpful is if you remember looking at domain and range or solving intervals, right? Domain and range, typically speaking, are best written as intervals, as the form a comma b, where of course maybe the endpoints might have brackets instead of parentheses, but they always go from smallest value to largest value. When you're looking on the domain, smallest to largest, that would go from left to right. So when you're trying to find the domain of a function, what I encourage students to do is look at the graph and identify the leftmost point and identify the rightmost point on your graph. Okay? In this case, this is my leftmost point and this is my rightmost point. That leftmost point would come down to some value on the x-axis. Let's say this value here. Notice that because that was filled in, this will get a bracket. And then over here, the rightmost point would be this value here, which is also filled in, so that gets a bracket. And then it's important to note that this graph is nice in the sense that there's no jumps or breaks or gaps. We will get every single x value because there's a point on the curve corresponding to every different x value in between the smallest and the largest value. And so that would be our domain set. It would go from A to B, which is this interval on the x-axis. To find the range, now we're going to be looking on the y-axis. Okay? So let's take a look at the y-axis. Again, we want to give typically domain and range in interval notation, so we always want to go from smallest to largest. On the range, that's going to go from the lowest point on your graph to the highest point on the graph. The lowest point on the graph happens to be this one right here. The highest point on the graph happens to be somewhere, it looks like right about there. That's the highest point on this graph. If we trace these over to the y-axis now, because we're looking for the range, this one would correspond to this y value. Notice that we do achieve that height because it's filled in. So that's going to be a bracket. And we get as high as this point, which is included. That corresponds to this y value. So that will be included. So that'll give us a bracket. And notice that we are able to achieve any y value or any height in between that smallest and largest because the graph has no jumps or no breaks in it. So this set here, let me say that this is a value of c to d. The range of the function would go from c to d included. So the big takeaway when you're looking for the domain values, you're looking for x values. And when you're looking for the range, you're looking at the y values. Okay. Let's get some practice with this. So we have the graphs here. We want to identify the domain and the range for each one of these functions. For graph A, let's start with the domain first. So we want to go from left to right. This is the leftmost point. This is the rightmost point. If we trace it to the x-axis, this goes to -1. This goes to 5. And notice that there's no gaps or no breaks in the graph. So we will get every single x value in between -1 and 5. So that makes the domain of that function -1 to 5. Let's now go ahead and find the range. For the range, we want to go from the lowest point to the highest point. This is the lowest point on the graph. This one just happens to be the highest point. On range, remember, now we're tracing over to the y-axis. This one goes to -4 and up to 2. And again, because there's no gaps or no breaks, we will be able to get every single y value in between -4 to +2. So our range set goes from -4 to 2, comma. Let's take a look at part B. One of the things you have to be very careful with when you read the graphs is to look to see, whether obviously points are included or not included. Those correspond to either open or closed circles, but then in addition, the presence of arrows can greatly impact things too. On the domain, again, it's always from left to right. One of the things that we see on this graph, because of the presence of this arrow, that indicates that that graph is going to keep going up and to the left forever. So this graph will always continue infinitely far to the left, and so as part of the domain, we're going to have all of the values tending towards -infinity. So that's how far to the left it goes. Now there is a rightmost point, and that rightmost point occurs at x equals to 3, which is included. And then once again, we're going to be able to get any x value in between -infinity and +3 because the graph is nice and connected. There's no jumps or breaks. So the domain on this one is from -infinity to 3. Let's now go ahead and talk about the range. For the range, again, go from lowest to highest. The slowest point on this graph is this one right here, which has a y value equal to -1. Now, how high does the graph go? Well, because of the presence of this arrow, that indicates that the graph is going to continue to rise and go up forever. So it'll go all the way up towards +infinity on the y-axis. So the range of this set, again, go from low to high on the x-axis, on the y-axis, is from -1 to +infinity. Let's take a look at the graph of C. The domain for this one, the graph goes as far to the left as this point. It goes as far to the right as that point on the x-axis. that's going to go from -3 to +4. On the range, we're going to look from low to high on the y-axis. This is the lowest point, and it's kind of a tie. Either one of these two will give us a high value of 2 on the y-axis. So the range for this one is from -1 to 2. That's an ugly looking one. Let me just pretty that up a little bit. There we go. -1 to 2 would be the range for that function. Let's go to the next one. I'm going to do these a little more quickly. In D, to talk about the domain, we're going from left to right. Leftmost point is here. That's at x equals to -3. The rightmost point would be this point here. That's at x equals to 1. So the domain is from -3 to 1, both included. Next thing we want to do is get the range. So we're looking from the lowest point to the highest point. This is the lowest point here. Corresponds to y equals to -3. This is the highest point here. That corresponds to y equals to +1. So the range is from -3 to 1. Again, be very careful. Even though you look at these two sets and they're the same collection of numbers, that domain set was one that belonged to the x-axis, whereas this range set was one that belonged to the y-axis. Let's now take a look at the graph of E. This one's kind of a little more interesting. We have a lot of stuff kind of going on here. Again, for the domain, we begin by looking for the leftmost point. Here, because of the presence of that arrow, that function is going to go down and to the left forever. So on the x-axis, this graph will tend all the way to the left towards -infinity, which always gets a parenthesis. Now, how far to the right does it go? Well, we do have a rightmost point, and that rightmost point is going to be the value 4, which will be included. Furthermore, we will get every single x value in the domain of this function between -infinity and +4, right? For example, over here, I can see that -3 is achieved by this point on the graph. It might be a little bit interesting to look at what happens, for example, x equals to 0. Is x equals to 0 in the domain? And the answer is yes, because if we just kind of zoom in maybe just for a minute, if I look at x equals to 0, what's happening here, even though the graph has kind of like this weird jump or break in it with like a closed circle and an open circle, here this point is not included on the graph, but certainly this point, the one that's above it, is. That's filled in, and that point, if I trace it down to the x-axis, does have an x value of 0, which means that 0 will be in the domain set. Same thing happens for x equals to 2. X equals to 2 is in the domain because this point is included, and this point has a x value equal to 2. So even though there's some jumps and breaks, we still take on every single x value from -infinity to 4, and so that's going to be our domain set. Let's now do the range of this graph. If we look at the graph, the range for it, because of this arrow, it's going to go all the way down towards -infinity. So there is no lowest point. It does have a highest point. It's any one of these, which is kind of a tie. These all take on the height y equals to 2. And it is an interval because we're not missing any y values. Okay. For example, if you look at the y value of 1, it's not achieved by either of those two, which is open, but there is a point over here to the left of the y-axis that's filled in and would provide us a height of +1. So for this graph, the range, it's everything from -infinity up to and including +2. So that would be the range set. Let's take a look at the graph of f. Again, we want to first answer the question of what is the domain, so we need to know how far left to how far right. Because of the presence of those arrows, that indicates that the graph is going to go all the way to the left. It also goes all the way to the right, and there's no breaks or anything in the graph. So the domain will include all x values from -infinity to +infinity, which oftentimes we call all real numbers. For the range, we now want to look at how low to how high. even though we do have the arrows here, this graph, if we look at the way the arrow is behaving, this graph is getting lower and lower and lower, and it's approaching the x-axis, which has a value of 0 on the y scale. However, this is what we call an asymptote, and something we'll cover later in the class. What this indicates is that this graph is always going to get lower and lower and lower, and closer and closer and closer to the value y equals to 0. But an asymptote like this is a line that the graph won't cross. So what that means is it's going to get as close to 0 as we like, but the 0 will actually not be included. So that's going to be an open circle. Now, how high does the graph go? Well, because of the presence of this arrow, that indicates that the graph is going to continue to rise and rise and rise forever, so it's going to approach positive infinity. Okay? So the range for this example is from 0 to infinity. The next thing we're going to look at is something called the vertical line test. The vertical line test is a visual test that can determine whether a given graph is that of a function. This is something similar to what we talked about earlier when we talked about different relations. Not every single relation defines a function. In particular, we need for each value of x to correspond to exactly one value of y in the range set. Vertically, what this would look like is the following. If any vertical line intersects the graph at more than one point, so for example, if I look at this graph here on the left, there's a single vertical line. That single vertical line would correspond to just one value of x. And what's going on here is that's intersecting the graph in 3 different places. That will give us 3 different y values. So that would be like x corresponding to one y value, the same x corresponding to another y value, and then an x corresponding to that last y value. So that one singular x is corresponding to more than one point in the range, and so that would not be a function. On the other hand, if every vertical line intersects the graph at most one point, then that graph would define that of a function. Okay? And so we call this the vertical line test. Anytime you use the vertical line test to determine whether a graph is or is not a function, please make sure you quote the name of the vertical line test. A lot of times you'll just see me abbreviate it. I'll just call it the VLT, short for vertical line test. Let's take a look at example 3. They want us to use the vertical line test to identify the graphs in which y is a function of x. If we look at graph A, we can quickly see that no matter what kinds of vertical lines I can draw some qualitatively over here to the left that don't intersect the graph at all. Some of the graphs in between, let's say -1 and +5, would intersect the graph in exactly one spot. And then over here, if I draw a vertical line beyond x equals to 5, it won't intersect the graph at all. Because of this, there's no vertical lines that intersect the graph in more than one place, so A is a function. So we would say is a function, and again, we would quote it because of the vertical line test. Very similar in part B, you can draw a bunch of different vertical lines just to get a feel for what's happening here, but no vertical line will intersect the graph of the function in B, so that is a function. By the vertical line test. Now we come to the graph of C, and there's a couple of different types of vertical lines you can draw, but in particular, it's very easy to find a line, a vertical line here, that intersects the graph in more than one point, and so this would not be a function. So not a function. And again, the reasoning is by the vertical line test. Take a look at D. If you apply the vertical line test to this one, the graph in D is a function. That one is a function by the vertical line test. This next graph is kind of interesting. Let me zoom in a little bit. Lot to kind of look at on this graph here, the graph of E. So if we start to draw some vertical lines, I can clearly see that over here to the left, we would get exactly one point of intersection. Beyond x equals to 4, it doesn't intersect it at all. And in between here, we kind of get clearly one defined point of intersection. What makes it interesting is if you look at, let's say, a vertical line at x equal to 0, 2, for instance. Let's look at this vertical line right here. The question is, how many points does that vertical line intersect that graph? And the answer is just one. It intersects it right here because that point is filled in, and that point is a part of the graph. However, if we look down here, that's an open circle. So that's not a point on the graph, which means that that portion of the line is not intersecting the graph at that place. So it turns out that this graph in E is also going to be a function by the vertical line test. So this one in E is a function. And again, the rationale is by the vertical line test, by the VLT. The last graph we have is that of an ellipse, kind of a very nice geometric looking object, but clearly this will fail the vertical line test. Here's a vertical line that intersects the graph in more than one spot, so this is not a function. Okay, it is not a function by the VLT. The next thing we're going to come to, which we've touched on lightly so far, are what we refer to as the zeros of a function. If the graph of a function x has an x-intercept at the point a comma 0, then a is called a zero of the function. And the terminology is an x-intercept. We use these terms oftentimes interchangeably. An x-intercept is going to be the same thing as the zero of a function. Simply what this means is if you take your function f, and if you plug in this x-intercept value, the value a, into the function, remember the y-coordinate is the value of the function, that gives us the output of 0. That corresponds to the ordered pair a comma 0, and on its graph, it would be an x-intercept. To find the zeros of a function, simply all we need to do is set the function equal to 0, and then solve. Let's take a look at example 4. Let's find some zeros for the given functions. In f of x, we want to solve where is f of x equal to 0. That is, where is 3x squared plus x minus 10 going to be equal to 0? For this one, it's a quadratic. We should try to factor it if it factors. I think we'll be in luck. It's going to be 3x and x. We can do a 5 and a 2, a positive and a negative, and that should work. So this quadratic does factor. Now that it's factored, we can set each term equal to 0. We have 3x minus 5 equals to 0, x plus 2 equals to 0. And now just solve each one of these equations individually. Add 5 to both sides, divide both sides by 3. We get 1, 0 is x equals to 5/3. For the second one, just simply go ahead and subtract 2 from both sides, and we get the 0, x equals to negative 2. Let's take a look at the next one. We want to find the zeros of g of x, which is equal to the square root of 10 minus x squared. To find the zeros, we're going to take the function, set it equal to 0. We need to solve where is the square root of 10 minus x squared equal to 0. This is one of our radical equations. To get the x by itself, we already have the radical isolated, so we can go ahead and raise both sides to the second power. So square both sides. On the left-hand side, the square root and the square cancel, so we get 10 minus x squared equals 0 squared is 0. From here, we can actually solve this quadratic by using the square root property because the x to the first power term is missing. So I'm going to add x squared to both sides. That will give us 10 equals to x squared. And then from here, to get the x by itself, we can just simply take the square root of both sides. And we get that x is equal to, the square root and the square cancel, and these do not simplify. We get plus and minus the square root of 10. So the zeros for this function g of x are at negative square root of 10 and positive square root of 10. The next one we have is the function h of t. To find its zeros, we're going to set it equal to 0. So when is h of t equal to 0? That happens when 2t minus 3 divided by t plus 5 equals to 0. We're now solving an equation that has fractions in it, so remember how we do this. The common technique is to multiply both sides of the equation by the LCD of any denominators you have. Here we just have one denominator, which is t plus 5. So let's multiply both sides of the equation by t plus 5. Over here, I'm going to put the t plus 5 over 1. And notice that that will cancel with our denominator as a factor of 1. So we're going to end up with just 2t minus 3 equals, on the right-hand side, 0 times t plus 5 will simply give us 0. We will see this kind of equation. So this is what we call a rational function. A rational function is just the quotient of two polynomials. And notice at the end of the day that when a rational function equals to 0, corresponds to precisely when its numerator equals to 0. So you can use this as kind of like a shortcut if you wish. And just thinking arithmetically, it makes sense, right? If you have a fraction, which part of the fraction has to be equal to 0 for the overall value to be equal to 0? And the answer is, well, it has to be the numerator. That's provided the denominator is not 0, but that will happen in this case. So we're now here. We just got to solve the resulting equation. We can add 3 to both sides. That will produce 2t equals to positive 3. Divide both sides by 2. And we get the solution t equals to 3 halves. The next topic we come to is that of increasing and decreasing and constant functions. You can see here the definitions of each of these concepts, increasing, decreasing, and constant. And there's a lot of terminology. Okay, let's kind of pick through it and see what all of this means. For example, a function is increasing on an open interval I if f of x1 is less than f of x2 whenever x1 is less than x2 for any x1 and x2 in the interval. That's a mouthful. What does that mean? Well, let's kind of break this apart a little bit. So the x1 less than x2, what that simply is saying is that whenever you read a graph like you would read a book, going from left to right. So if we have two x values, let's call the first one x1, let's call the second one x2, we want to make sure that we're reading it going from left to right. So the second x value is going to be bigger than the first x value because we're moving to the right on the x-axis. And then what does it mean for the graph to be increasing? Well, what that means is that the height at the first point, which we're calling f of x1, is going to be less than the height of the graph at x2, which is given by f of x2. So if you're comparing these values on the y-line, remember the higher value is always bigger. That means that f of x2 is greater than f of x1. Okay. Intuitively, it's pretty easy. Simply put, if you're reading a graph going from left to right, if the graph is moving in an upwards direction, as this one is, then the graph is increasing on that interval. Similarly, if you read a graph going from left to right, if the graph is moving in a downwards direction, then the graph is said to be decreasing on that interval. In this case, again, we still have x1 is less than x2. We're still going from left to right, but the difference here is that the curve is higher at the initial point and lower as you go to the right. So f of x1 is actually greater than f of x2 when a graph is decreasing. And the last possible scenario is that the graph can be constant. And a graph is constant if every value of x in the interval produces the same output. So the height of the curve at x1 would be given by this number. Let me just make up a value. Let's say it's going to be 3 on the y-axis. If I plug x2 into the graph, we also get out the same input. And visually what you would see is that a graph is constant if the portion of that graph is horizontal on that interval. Okay? So increasing, simply put, always read a graph like you read a book. Go from left to right. If the graph is moving upward, the graph is increasing. As we go from left to right, if the graph is moving downward, it's decreasing. And if the graph is flat, straight across, then the graph is constant on the interval. The other thing that's going to be very important whenever we give intervals of increase, decrease, or constant is that these are always intervals in the domain. Okay? So when we say state the intervals for increase, decrease, or constant, these intervals are always on the domain, so we're looking on the x-axis. My advice whenever you're doing this is to simply begin, go from left to right, and at each point in time just identify what you see that the graph is doing. For example, in the graph of A, let's start out. So if I go all the way to the left, now this graph goes all the way towards negative infinity because that arrow that's moving up and to the left. So this graph goes all the way towards negative infinity. Now initially, if I start going from right to left, what's happening here is that the graph is going down. So I'm reading it from right to left, and the graph is going down, 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 and it continues to move down until we get to x equals to 0. So what's happening here? This graph is decreasing on the interval negative infinity to 0. Also, too, whenever we're talking about intervals of increase and decrease, the endpoints are not included. Those are going to be points where oftentimes the graph will change behavior from increasing to decreasing or vice versa. And so those points don't get included in either of the types of behavior. Let's continue to read our graph. We're now going to continue to go from left to right. And now one of the things that we notice is that now immediately after x equals to 0, this graph begins to move up. And it continues to move up until we hit the value x equals to 2. So the graph is rising in between x equals to 0 and x equals to 2. So that's an interval of increase. So it's increasing between 0 to 2. And now what happens after x equals to 2? Well, after x equals to 2, this graph is now going to go down and down and down and down. And because of that arrow, it's going to continue to move down forever. So this graph is going to be decreasing from 2 to positive infinity. And when you have multiple intervals of increase or decrease, typically we will add the union sign in between because it means this interval or that interval. So we've now completely described the increase and decrease intervals for this graph in part A. And again, just do it by going from left to right. As the graph does one behavior and changes to the next, just categorize what you see. Let's take a look at the next one. Here, initially, if we start off all the way to the left, this graph is horizontal and constant until we hit the x value of 0. So this graph is going to be constant on the interval negative infinity to 0. Again, those are always intervals on the x-axis. Now, what happens after x equals to 0? Well, after x equals to 0, if we continue to go to the right, the graph is now moving in upwards direction, and because of that arrow, it'll continue to go up forever. So this graph is increasing from x equals to 0 to positive infinity. And that gives us the intervals of increase, decrease, and constant for this one. The next important concept we're going to talk about is that of a relative maxima or relative minima. And the keywords relative here are very specific. Some books will also use the term local max or local min. We say that a function value f of a is a relative maximum of f if there exists an open interval containing a such that f of a is greater than f of x for all x not equal to a in the interval. Okay? Again, it's a pretty wordy definition. Let's break it down and see what it means. Okay? Visually speaking, these are kind of easy to see with your eyes. what you're looking for is points on the graph that are either high spots or low spots. In particular, if we're looking for relative maximums, we're looking for like high spots or like tops of hills or crests or something like this. If I look at this particular point on the graph, okay, and I kind of zoom in, and I can form an open interval on the x-axis, okay, that means you're going to do a little open interval about A, where you kind of restrict and you zoom your attention into just that portion of the graph, okay. So you can forget everything else that's going on, and we want to zoom in on just what's in that box. With respect to what's in that box, that kind of relative little region of the graph, this value, f of a, is the largest output from every value that you could get out of the function nearby it, which means that f of a would be what we call a relative maximum. Okay. The reason why it's called a relative maximum, as opposed to just the word maximum, is that notice there will be higher points on this graph. Because of this arrow, this graph will go up and up and up and up forever. So there will be many function outputs that will actually be larger than f of a. But relatively speaking, within regards to just the region nearby it, if I just restrict our attention to an open interval containing a, f of a would be the largest thing next out of everything next to it, and that's what makes it a relative maximum. Similarly, if we look at kind of like this low point on the graph over here, if I draw an open interval around the value x equals to b, and if we restrict our attention to just that open interval or that window of this graph, this output, that f of b value from that ordered pair, is smaller than any of the function values nearby it, and we would refer to f of b as being a relative minimum. Let's take a look at example 6. We're asked to find all of the relative minimums and maximums for the function given below. In order to do so, what we want to do is identify kind of like those high points and those low points. So this graph's going to have quite a few. So for example, here's kind of like a low point at this value. This is like a high point. We have a low point here, and then we have like another high point here. Okay. This value here is the value -2. So we have a relative max of -2 because it's actually the function value, and this occurs when x equals to -3. So you can say it a couple of different ways. You can say a relative max -2 at x equals to -3, or if you wanted to use the function notation, you could word it like this. You can say f of -3 equals -2. The thing to keep in mind, I sometimes will avoid this notation because I think some students will kind of get confused. The maxima or minima value itself is actually the function value, okay? So the relative minimum in this case, oops, I wrote it in the wrong spot. That was a low point. That should be down here. Sorry, everybody. That relative minimum here, that low point, it occurs at -3, but the actual max min value itself is the -2 value. The x coordinate just kind of simply tells you where that value occurs at. So instead of using the function notation, a lot of times what you'll see me do is I'll just say the actual value and just say where it occurs at. So I typically like to write mine as a relative minimum of -2 at x equals to -3. We now have a relative maximum. The relative maximum is the y value of 2, and this occurs when x equals to -1. We have a minimum value here. The minimum value is -6, and that occurs at x equals to 2. And then lastly, we have a relative maximum of 5, and this is occurring when x equals to +4. So whenever you're identifying these points, whenever you're looking at your ordered pairs from those high or low points, technically speaking, the extreme value is the y value, which is the function output. We also do want to, so I do want to see this information included, whether you write it as like f of negative 3 equals to negative 2, or you write it like I have over here, in addition to saying what the max min value is, we also want to give its location too. Let's take a look at example 7, kind of putting it all together now. In example 7, we're asked to give the intervals of increase and decrease, and also to find the relative max and relative minima. So let's start off with this graph. We will get a couple places where we're going to have some increase and decrease. And to do so, again, just begin by reading the graph. Let's go from left to right. When we start to read the graph going from left to right, we see that initially the graph is moving in an upwards direction. So the graph is moving up and up and up and up, and it continues to move up until we hit the x value negative 2. So this graph is increasing from negative infinity until we hit negative 2. Now, what happens after negative 2? If we continue to read the graph, now it's going down and down and down and down, and it continues to move down until we get to x equals to 0. So it's decreasing in between negative 2 and 0. We now continue to read the graph. From x equals to 0, now we're initially moving up, 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 and up, and we continue to move up until we hit x equals to 3. So it's increasing from 0 to 3. And now after 3, the graph will continue to decrease from 3 and on. So that's going to be from 3 to positive infinity. So we have our intervals of increase, decrease. Let's now go ahead and look for our relative max, relative min. We have a high spot right here, a low point right here, and a high point right there. So this is going to be a relative max. The value is 4. And this occurs when x has the value negative 2. So relative max of 4 at x equals negative 2. Here we have a relative min. The y value is 1. And this occurs when x equals to 0. And then we do have a relative maximum here as well. That relative max value is 2. And it occurs when x equals to positive 3. So relative max of 2 at x equals to 3. The next topic we're going to cover in this section is even and odd functions. So these are our functional relationships. It's very different than, for example, if you work with, like, let's say, integers or whole numbers. Most of us are kind of used to a number being either even or odd. With functions, that's not necessarily the case. If a function is even or odd, it's a very special property. You can be even, odd, or neither. So it's not a dichotomy here. A function doesn't have to be one or the other. There are many functions that don't satisfy either of these properties, and we refer to them as neither. But having a function that's either even or odd means that it has quite a bit of special properties about it. For example, a function f is referred to as being even if f of negative x is equal to f of positive x for all values of x in the domain of f. Simply put, what happens is whether you plug in the positive of an x value or its opposite, you get the same output. So the function f evaluated at negative x would be the same as the function f evaluated at the positive of x. Conversely, a function is odd if f evaluated at negative x is the opposite of the function evaluated at positive x for all x in the domain of f. So if we're given a function, how can we tell if the function is even, odd, or perhaps neither? Well, there's a test for this. What we want to do is take the original variable x and replace it with negative x into the function and simplify. Once you do this substitution and you simplify, we want to see what results. If, after substituting, if your new expression is equal to the original, then that would tell us that the function is even. If we don't recover the original function initially, the next step would be to try to factor out a negative. If you're able to factor out a negative from the new expression and that then recovers the original, in other words, if we get the opposite of the original, then that would tell us that the function is odd. If after factoring out the negative we're still not able to recover the original, then we would say that the function is going to be neither. Let's take a look at example 8. We're asked to determine whether each function is even, odd, or neither. For the function in part A, we're going to begin. We simply go ahead and we're going to take, and everywhere we see an x, we need to replace it with negative x. So everywhere we have x, we put negative x. We now want to simplify this. Negative x cubed means negative x times negative x times negative x. That will give us a negative x to the third. Over here, negative 6 times negative x will give us positive 6x. So we plugged it in, we simplified it. Then now what we're going to do is we want to check to see, is this equal to f of x? And what we now have, this is not the same thing as the original function. The only thing we can conclude about that is that means that f is not odd. Excuse me, it's not even. So we substituted in the negative of the x. We simplified it. We did not recover the original function. So it's not even. The next step would be to try to now take that expression and factor out a negative 1 from it. If I factor a negative out of what we have, this would give us x cubed minus 6x. Right? Factoring out a negative changes the signs. And now let's look at what we have. This piece here, x cubed minus 6x, that was the same thing as our original function. So what we've discovered is that when we plug in negative x into the function, it ends up equaling the opposite of the original, and that means that the function f is odd. So f is an odd function. So we have an odd function here. Let's do the same thing. The test always works the same way. We now want to determine whether g is even, odd, or neither. So we begin by substituting in negative x for x. Like this. Negative x to the fourth will turn out to be positive x to the fourth. Minus 5 times negative x squared, that's just x squared. With that negative plugged in, we check, and we actually have recovered. This is the same thing as the original function f of x. So what this shows, actually g of x is the name of this. This is equal to g. So what this shows is when we plug in g of negative x, it's the same thing as g of positive x, and that would tell us that this function is even. So g is an even function. So g is even. Let's take a look at one more example. In example 9, we want to do the same thing. We want to determine whether h of x is even, odd, or neither. To begin, let's go ahead and swap out the x for negative x. So everywhere we see an x, we're going to put negative x. And then we immediately want to simplify that. This should become x squared minus 2x plus 1. We do a quick check. This is not the same as h of x. We did not recover the original starting function. So that tells us that h is not even. The next step is we now want to try to factor out a negative. That will give us negative x squared plus 2x minus 1. if we look at the thing after we factored out the negative, that is not equal to h of x either. So h of negative x is not going to be equal to the negative of h of positive x either. That tells us that h is not odd. So this is going to be an example of a neither function. So h of x is neither. The next thing we're going to discuss is some certain symmetry properties of even and odd functions. A graph is symmetric with respect to the y-axis if for every point x comma y on the graph, the point negative x comma y is also on the graph. Visually, this will tell us that the graph will look like its mirror image when reflected across the y-axis. It turns out that even functions will exhibit this type of y-axis symmetry. The graph of an even function is those for which f of negative x equals to f of positive x, and these graphs will be symmetric with respect to the y-axis. Knowing that a graph is even and that it has y-axis symmetry really allows us to kind of cut down on the work later on when it comes to graphing these things. If you have, let's say, a portion of this graph, let's suppose I know the graph of this function for x greater than 0 if I know that it looks like this. If we also know that the graph is even, then I can find the other half of the graph by simply reflecting it across the y-axis. Visually speaking, what this means is if I have any point on the graph, x comma y, if I connect that point to the y-axis by going straight horizontally, if I proceed the same distance on the other side to the point located at negative x comma y, that will produce another point on the graph. So even functions exhibit a y-axis symmetry. If a function is odd, it has a separate type which is referred to as an origin or a point symmetry. A graph is symmetric with respect to the origin if for every point x comma y on the graph, the point negative x negative y is also on the graph. Visually, the graph will look like its double reflection, first across the y-axis and then across the x-axis. Okay? So origin symmetry you can think of as being a hallmark of odd functions. Essentially what that's telling us is the following. So for a point symmetry, if this graph is symmetric about the origin, then pick any point on the graph. If you take that point and you connect it to the origin via a straight line, then continue that line going in the same direction. The distance between the original point and the origin, whatever that distance is, if you proceed the same distance on the other side, you will hit another point that is on the graph. In other words, if you have the point x comma y, formed by going to the right and going up in this case, if you go the opposite x value, so go to the left negative 2, and go the opposite y, go down 3-ish, you would find another point on the graph. You can think of origin symmetry in addition, so this is the proper way to view a point symmetry. You can also view it as a double reflection. Okay. So again, let's suppose that I know that this graph is symmetric with respect to the y-axis. Excuse me, symmetric with respect to the origin. So I have this portion here. If you do a double reflection, and you can do it about any axis first, if I first reflected about the y-axis, it would look like this. If I then take it and reflect it about the x-axis, this part would reflect down, and then that would give you the other part of your graph. Okay? So an origin symmetry can also be thought of as a double reflection. In example 10, they give us some partial graphs, and they ask us to complete the graph based upon the symmetry. In part A, they tell us that f is even. Remember, even functions should have a y-axis symmetry. So if I know that this graph is symmetric with respect to the y-axis, then all I have to do is go ahead and reflect it across the y-axis, which would look like this, and that would give us the remaining part of the graph. Again, if f is even, then what that means is that we're going to have both the point x, comma f of x, and negative x, comma f of x on the graph. Remember, it'll have the same height because f of negative x is equal to f of positive x. So if we have the point 8 comma negative 2, then what, positive 8, negative 2, then what that's telling us is that if I plug negative 8 in, I'm also going to get negative 2 out. For the next one, if they tell us that f is odd, then this is going to be an origin symmetry. Again, the best way to kind of graph those is to do the double reflection. If we take this part of the curve, we can first reflect it across the y-axis, which is what we just did a minute ago. So first about the y, and now we're going to take it and reflect it about the x-axis, and we would get this graph right here. Easy way to kind of determine what kind of points you end up getting on this graph. If we know that the point 8, negative 2 was on the first part of it, then the other one, which is going to be negative 8, positive 2, will be on this. Easy way to kind of think of it is that x and y both change sign. So the positive 8 becomes a negative 8, the negative 2 becomes a positive 2, and this will be a graph that has an origin symmetry. The last topic we're going to talk about in this section is what's referred to as the average rate of change of a function. Let's suppose we have 2 points on the graph of f. Let's say x1 f of x1 and x2 f of x2. The average rate of change of f from x1 to x2 is given by the formula f of x2 minus f of x1 divided by x2 minus x1. And if you're looking at this, that formula might sound a little bit familiar, in particular of like y2 minus y1 divided by x2 minus x1. Some of you might remember that from an earlier class as being the slope of a straight line connecting 2 points. And graphically, what this average rate of change represents is the slope of the secant line that passes through the 2 points. So if I look at the rate of change of this function between x1 and x2, here this function is kind of increasing for a portion of its domain, and then it's kind of decreasing. But what we're asking is, like on average, because at certain points it's going to be increasing more than others, on average, what is the rate of change between these 2 points, x1 and x2? And the average rate of change is kind of like the steady change. So instead of going from f of x1 to f of x2 in kind of like this variable path, what if we just kind of went along a straight line path, which is what we call the secant line, and the slope of that secant line, that's the thing that represents the average rate of change of the function. Let's try this. In example 11, we're asked to find the average rate of change of x squared from x1 equals to 0 to x2 equals to 1. Okay. So my advice is anytime you hear that buzzword, if you hear like a specific formula, immediately go ahead and write it down. F of x2 minus f of x1 divided by x2 minus x1. Here it's going to be f of 1 minus f of 0 divided by 1 minus 0. Now in the numerator of this expression, that does involve some function evaluations. And anytime I do my average rate of change calculations, I always like to kind of do those pieces like off to the side. For this particular function, we have f of x equals x squared. If I plug 1 into the function, we're going to get 1. And if we plug 0 into the function, we just so happen to get out 0. So this is going to be 1 minus 0 over 1 minus 0, which is 1. So we get 1 over 1, which is 1. So the average rate of change of the function f of x equals x squared from 0 to 1 would have an average change of 1. Let's do the same thing. Let's find the average rate of change from 1 to 3. That's going to be f of 3 minus f of 1 divided by 3 minus 1. 3 minus 1 we know is 2. Again, to keep the workflow nice and clean, let's evaluate these off to the side. The function value f of 3 is going to be 3 squared, which is 9. F of 1 we already did a minute ago. We know that f of 1 is equal to 1. This is going to be 8 over 2, which is an average rate of change of 4. Let's do one more. Let's find the average rate of change of this function, 3x minus 4, from negative 4 to 5. This is going to be f of 5 minus f of negative 4. Be very careful with your parentheses here. The denominator is x2 minus x1. x2 minus an x1 value, which itself is negative. So minus and minus will turn into a plus ultimately. We're going to have a 9 in the denominator. Again, off to the side, let's work out these function values. We need f of 5 and f of negative 4. F of 5 is going to be 3 times 5 minus 4, which is 15 minus 4, which is 11. F of negative 4 is 3 times negative 4 minus 4, which is negative 12 minus 4, which is negative 16. To finish it off, 11 minus a minus 16 is the same thing as 11 plus 16, which is going to be 27 over 9, and 27 divided by 9 is 3. So the average rate of change of the function 3x minus 4 between negative 4 to 5 has an average rate of change of 3. Let's see if we can calculate the average rate of change of this function between 2 and 9. Again, this is going to be f of x2 minus f of x1, all divided by x2 minus x1. 9 minus 2 we know is 7. In the numerator, we do have those function values to work out. Let's work those out. Excuse my dog, everybody. He's trying to crash the lecture here. So let's go ahead and work these out. So we want to find the value for f at 2. F at 2 is equal to 3 times 2 minus 4, which is going to be 6 minus 4, which is 2. And f of 9 is 3 times 9 minus 4, which is 27 minus 4, which should be 23. So we have 23 minus 2. That's going to be 21 over 7. And 21 over 7 equals to 3. So we get an average rate of change of this function of 3. What's interesting for this particular example is if you kind of compare the answers to part A and to part B, is notice that we got the same value. We got the value of 3 and 3. That's no coincidence. If we go back and look at the function that we had, this function here, f of x, which is equal to 3x minus 4, that's a linear function. That is of the form mx plus b. And we know that a straight line, the slope or the rate of change between any 2 points is always the same, and that's the value that's the slope. And notice that the slope of this equation so happens to be positive 3, which matches up with exactly what we got from the average change over the intervals given in part A and part B. The last little comment we'll make, which is kind of important, and this kind of illustrates exactly where the difference quotient comes from, as I promised I would disclose earlier, is that if you take the average rate of change of the function between, let's say, x and x plus h, that corresponds to that slope of the secant line. That's where the difference quotient comes from. If I use f of x2 minus f of x1, that becomes f of x plus h minus f of x, all divided by x2 minus x1, which is x plus h minus x. Notice that the x's in the denominator cancel, and we're simply left with that quantity h on the bottom. So the difference quotient in itself is actually a specific average rate of change, which is the slope of the secant line of the function between x and x plus h.